morning everyone. Myself Dr. Mydeen Bibi, Assistant Professor of Mathematics from Masaka College for Women. I am here to give some detailed explanations regarding norm space. Functional analysis is a branch of mathematical analysis dealing with the functionals or functions of functions, and the core of which is formed by the study of vector space endowed with some kind of limit related structure. The basic and historically first class of space studied in functional analysis are complete normed vector spaces over the real or complex numbers. In this lecture, we are going to give three learning objectives. That is, one is norm space, the next one is example of norm space, and the third one is theorems on. First of all, I want to give the definition of norm space. A norm on x is a function norm from x to r such that for all x comma y belongs to x and k belongs to k. We need to satisfy the three conditions, that is norm x is greater than or equal to 0, if norm x is equal to 0 if and only if x should be equal to 0. Norm x plus y is less than or equal to norm x plus norm y, and norm kx equal to modulus of k into norm x. The norm space is a linear space with a norm on it. For x and y belongs to x, let the d of x comma y in the metric, we are defining that d of x comma y equal to norm x minus y, where d is a metric space on x. Examples of norm spaces. The first one is space is k power n. For n equal to 1, the absolute value function norm is a norm on k. Since norm k equal to modulus of k into norm 1 for all k belongs to k, it follows that any norm on k is a positive scalar multiple of the absolute value function. Let p greater than or equal to 1 be a real number. For x is equal to x of 1, x of 2 and so on x of n belongs to k power n. Let norm xp be defined as modulus of x of 1 to the power of p plus and so on modulus of x of n to the power of p the whole power 1 by p. If p equal to 1, then norm 1 is clearly a norm on k power n. If p greater than 1, then letting aj equal to x of j and bj equal to y of j. In Minkowski's inequalities, it follows that norm of x plus y is less than or equal to norm xp plus norm yp. Hence, norm p is a norm on k power n. The next example of norm space is sequence spaces. For 1 is less than or equal to p less than infinity, consider the set LP of scalar sequences. For x is equal to x of 1, x of 2 and so on in L power p, let norm xp equal to modulus of x of 1 to the power of p plus x of 2 to the power of p plus and so on the whole power 1 by p. If p equal to 1, the L power 1 is a linear space and norm 1 is clearly a norm on it. If p greater than 1, then letting n tends to infinity in Minkowski's inequality, it follows that norm x plus yp is less than or equal to norm xp plus norm yp, so that LP is a linear space and norm p is a norm on it. The next important example of norm space is measures in measures integration. LP spaces. Let M denote the Lebesgue measure on R and E be the measurable subset of R. For 1 is less than or equal to p less than infinity, consider the set LP of E of all equivalence classes of p integrable functions on E. For x in LP of E, let norm xp is equal to integral over E modulus of x power p dm the whole power 1 by p. Again, we are mentioning for p equal to 1 and p greater than 1. If p equal to 1, L1 of E is a linear space and norm 1 is a clearly norm on it. If p greater than 1, the Minkowski's inequality implies that for x comma y in LP of E, norm x plus yp is less than or equal to norm xp plus norm yp. Hence, LP of E is a linear space and norm p is a norm on it. The last two examples of norm spaces are function space and inner product space. The first one is function space. Let T be a set and let B of T denote the set of all bounded scalar valued functions on T. For x in B of T, let norm infinity supremum of modulus of x of T. The norm infinity is a norm on B of T. Also, it is known as the supremum norm. The next one is inner product space, and inner product space is a linear space with inner product on a linear space X. It behaves as a dot product on a linear space X. It behaves as a dot product on R squared. Like norm x is equal to inner product of x comma x the whole power 1 by 2. This is a linear space and a norm on X. Next, we are going to see about theorems on norm spaces. The first one is very important Rees lemma we are going to see now. Let x be a norm space and y be a closed subspace of x and y not equal to x. Let r be a real number such that 0 less than r less than 1. Then there exists some xr belongs to x such that norm xr is equal to 1. And this here we are going to find the distance of xr under the closed subspace y. and r is less than r is less than distance of x r comma y, which is less than or equal to 1. And the another one important thing is the subspace completion, that let x be a norm space and y be a subspace of x, and x belongs to x and y belongs to y and k belongs to k. We have norm kx plus y is greater than or equal to modulus of k into distance of x comma y. Let y be a finite dimensional, then the closed subspace y is complete. In particular, it is closed in x. In the theorems on norm spaces, we are going to give the equivalent conditions too. Let x be a norm space, then the following conditions are equivalent. The first one is every closed and bounded subset of x is compact. The subset set of all x belongs to x, norm x is less than or equal to 1 of x is compact, and x is finite dimensional. Also, the another theorem on norm space is let x be a norm space if E1 is open in x and E2 is contained in x, then E1 plus E2 is open in x. Let E be a convex subset of x, the interior of E and the E closure also convex. If E interior is non-empty, then the E closure is equal to E interior. Let y be a subspace of x, then y interior is non-empty if and only if y equal to x. In this session, the theorem on norm the space, the last one is stronger, comparable and equivalent. First of all, I want to give the definition regarding stronger, comparable and equivalent. The norm is said to be stronger than the norm dash if the metric d is stronger than the metric d dash. Like that, if the norm and norm dash are said to be comparable if one of them is stronger than the other, and they are said to be equivalent if each is stronger than the other. In this definitions regarding, I am going to give on applications that two norm theorem, that is norm and norm dash be norms on linear space x, then the norm is stronger than the norm dash if and only if there is some alpha greater than 0 and norm x dash is less than or equal to alpha into norm x for all x belongs to x. Further, the norm is equivalent to the norm dash if and only if there are alpha greater than 0 and beta greater than 0, such that beta norm x is less than or equal to norm x dash is less than or equal to alpha norm x for all x belongs to x. I hope you all gather lot of things regarding norm space. Thank you so much.